In this problem, we're trying to take a motor with some measurements and calculate the equivalent circuit parameters. So typically when you're doing this, there's three conditions that they use sometimes. The no load case, where you're basically letting the motor go as fast as it can, and that you apply the full voltage. The blocked rotor, where you're holding the rotor and you're basically increasing the voltage until you get to the max rated current. And the other one is the rated condition, where you're operating it at a high efficiency point. In most cases, you do get the no load and the blocked rotor case. So that's what we have in this case. So we have to figure out in these two cases which part of the equivalent circuit can we eliminate to figure out which parameters to solve to make it a little bit easier to solve. So the first thing that we want to look at is that it says that we measure the DC resistance to be 5.6 ohms line to line. So we can kind of see that we're basically have a three-phase system, and we have these windings which have some series resistance. And we're coming in here and we're measuring the resistance between these 2 points. So you can kind of see that that's going to go through two of the resistors. So our stator resistor is going to be equal to the 5.6 ohms divided by 2. So first of all, we have our stator resistor is equal to 2.8 ohms. Okay, so we're good. Everything's good on that. Now we want to look at the no load case and the full load case. So in the no load, this is going to be a slip that's approximately 0. Okay, because it's going as fast as it can, so there's nothing slowing down the motor, so the motor's going to go about approximately as fast as that. So when we do that, then we see that we get our rotor resistance divided by S is approximately equal to infinity. So this is going to be our equivalent circuit. So we convert that from line to line into line to neutral. This is the 2.8 ohms. And this is JX1. And this is going to be JXM. Now the other path going this way has the R equal to infinity, so it's going to drop off. So this is our no load case. Now we're going to go into our blocked rotor. In the blocked rotor case, then S is equal to 1 because our motor isn't moving at all. So we can see that this is equal to omega synchronous minus 0 over omega synchronous, so that's equal to 1. So in this case, we have 723 divided by the square root of 3, and then we have 2.8 ohms. We have JX1, JXM, JX1, and our rotor. Since the S is equal to 1, we just get that. So these are our two circuits, and we're using these two circuits to solve for the X1, the XM, and the R rotor. Okay, so in order to simplify things down, the resistance, the magnitude of JX1 plus RR is typically much, much less than JXM. So in this case, we can ignore our JXM. So we get this simplified equivalent circuit. So you see we can neglect that because those two are in parallel. When you get a big one in parallel with a smaller one, the smaller one dominates. Okay, so now we can start plugging everything in to see what's going on. So we have our voltages, our currents, and our powers. Let's start with the no load case. And if we start with the power, you can kind of see that our power is going to be equal to 3 times I magnitude squared times RR. So this is equal to 3 times 4.5 times 2.8. And so then this is equal to 170 watts. Now, if this, and so there's 170 watts. If this was larger than, if this power here was larger than this power, then that would be the loss that we get from friction and windage and all that kind of stuff. In this case, there's no friction loss or the friction loss is negligible in the motor. Okay, so now we're going to use our voltages and currents. So now we have the V over I magnitude is going to be equal to the 2.8 squared plus the xm plus the x1 magnitude squared. And then this is 2200 and 4.5. So we get 2200 converted into line to line. So we see that xm plus x1 is equal to 282 point, well, let's just do 282.2. Okay, but that's both of them. So let's jump over to our other case over here. Okay, and so now we're going to start with our power. Okay, so then our power, like we had before, is 3I squared times 2.8 plus RR. Okay, so then this is equal to 25. So 3 times 25 squared times 2.8 plus RR, and that was 9,000. Yep. Okay, so then our rotor resistance is going to be equal to 9,000 divided by 3 times 25 squared minus 2.8. And so we have a rotor resistance of 2 ohms. So let's box that one. That's another one of our answers. Okay, so now we want to look at our resistance or our impedance like we did in the other case. So this is 723 over the square root of 3 times 25 is equal to V over I, which is equal to the square root of 2.8 plus 2 squared plus 2x1 squared. And then we take the square root of all of that. So now we see that 2x1 quantity squared is equal to 723 divided by the square root of 3 times 25 quantity squared minus 4.8 squared. So we solve this for x1. So we solve that and we get x1 is equal to 8 ohms. And then we can take and plug this part into here, and we get that xm is equal to 282.2 minus 8. And we get xm is equal to 274.2 ohms. So now we have our xm, our x1, our rs, and our rr. And we are all done. Let's go ahead and draw the circuit just to be complete. And we are, go ahead and box that. There is our equivalent circuit, and we are all done.